So this is going to be our discussion of alternating series that is in your book, the Stuart Kokoska Text Online, section 9.5, page 692 to 698. Let me encourage you again to really make an attempt to read this. You're not going to find a more readable textbook than this one, and developing the skill of being able to read a college textbook is going to be really useful to you when you're trying to get through college and you maybe have some professors who aren't, very diligent about explaining things clearly. Then you can look back into the book and read it for yourself and understand it for yourself. All right, so that's one thing you should do is try and read that. Now, Here's why we're talking about alternating series, all right? Alternating series are series that go positive and negative. So one thing that we're going to notice is we already have 3 tests for convergence of a series. And these tests are the comparison test, the limit comparison test, and the integral test. Now these tests, all 3 of them have something in common. They all require that a sub n and b sub n are greater than 0. So they only work for a series with positive terms. But you could have a series with negative terms. So in a series, remember the domain of the series, which is the n, is only natural numbers. So natural numbers are all positive and have no fractions or decimals. But a and b, the value of each sequence member, can be any real number. So they can be positive, negative, rational, irrational. They can be anything. All right, so that's the domain of the sequence. So you certainly could have sequences that don't have positive values, and some of the ones that we're going to be really interested in have negative values. So we're going to talk about what we can do with sequences that have some negative values. So first of all, let's talk about, for comparison, we know about this sum, the sum from n equals 1 to infinity of 1 over n. That's called the harmonic series. And we know that the harmonic series diverges. And so what that means to us is that if I do 1 plus 1 plus 1/2 plus 1/3 plus 1/4 plus etc., and I keep adding that forever, that diverges. All right? But what if instead of doing 1 plus 1/2 plus 1/3 plus 1/3 all plus, what if I go 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. So I keep alternating the signs of the terms like that. Does that converge or diverge? That's going to be our question. So that is what we're really looking at, is the sum from n equals 1 to infinity. Now, there's a standard way to get this sort of alternation of signs. So what you do is you put in a factor in your sum of -1 to the n minus 1 power. So you're going to see how that generates the alternating signs, because when n equals 1, I have -1 to the 0, which is +1. When n equals 2, I have -1 to the 1, which is -1, so that gives me the negative sign. When I have n equals 3, I have 3 minus 1 is 2, so -1 squared is +1, that gives me the positive. And as the n's increase, I'm going to have alternating positive and negative. So then, for example, if I wanted the first term to be negative, then what I would do is just drop the -1. So using the -1, the n minus 1, allows me to start from n equals 1 and start with a positive. So you'll see sometimes people will drop this -1 and put a 0 there, even though technically 0 is not a natural number, so it's outside of the domain of what a sequence should have. But that's not really catastrophic, because you can sort of pull out that first 0 term and then look at the rest of the terms. So there are ways to work around it. So you will see sometimes we'll have 1 to infinity, -1 to the n minus 1. Some people put n equals 0 to the infinity, -1 to the n. You just have to look at it and think, is the first term going to be positive or negative, and work it out from there. All right, so now that's just the alternating, and then what I do is I multiply it times 1 over n. So that's this. If I have this sum, that gives me 1 minus 1/2 plus 1/3 minus 1/4. You can work out a few terms of that if you want to convince yourself of that. All right, so this is called the alternating harmonic series. So our question is going to be, does that converge or not? All right, so what we're going to do is we're going to do an analysis of that, a graphical analysis that's fairly simple. And also, instead of just looking at this sequence of 1 over n, we really be looking at any alternating sequence at all. So what we'll do is we'll look at when n equals 1, so this is like an n axis, and this is going to be, we're going to track the partial sum, so this is going to be s sub n up here. So if I do one partial sum, that means I'm going to forget about all these things and just look at the first term. It's going to be 1. So in general, it's going to be whatever my first term is. So that first term, we're going to call it b sub 1, just sort of conventionally. Our question is whether the sum from n equals 1 to infinity of negative 1 to the n minus 1 b sub n converges or not. And what we're looking at is partial sums here. All right, so well then what happens next is I add negative 1/2. So when I add negative 1/2, what happens is I'm going to start from the partial sum that I had before, and I'm going to drop down 1/2. Now, in this example, it's 1/2, but it doesn't matter what the sequence is. I'm going to get my next term, s sub 2, by subtracting b2 from my b2 being just the positive part, by subtracting 1/2, in other words, from the sum that I had. And that gives me actually I wrote s sub n here, but it's actually s sub 2. So then you can see that if I want to get s sub 3, I just start from s sub 2, and I'm going to add 1/3 to it. Now 1/3 is smaller than 1/2, so a critical issue is I'm coming up less than I went down. So I come up by b sub 3, which is less than I went down, and that gets me to my s sub 3. And then I just keep doing that. So I'm going to drop b4, drop down b sub 4, and that gives me s sub 4. And then I'm going to come up an amount b sub 5, and that's going to give me s sub 5. And so you can kind of see what's happening here is the sums are going up and down, but they're going up and down by a lesser amount each time. And that's the key to the convergence here. Since I'm always going, for the harmonic series, because 1 over n is decreasing, I'm always going up and down by a smaller amount. And what's going to be trapped in between those two is the actual sum, right? The sum of infinitely many terms. So we're always going to be going with the s sub n's above and below the actual sum. And because the this particular sequence is decreasing, we're going to eventually converge on this s, and we're going to have a convergent series. So what that depends on is that the b sub n's are decreasing, and the limit as n approaches infinity of the b sub n's is 0. So here's what we get. We get that the sum from n equals 1 to infinity of negative 1 to the n minus 1 b sub n converges if b sub n is decreasing and limit as n approaches infinity of b sub n equals 0. So what you ultimately get here is that for alternating series that alternate positive and negative, you get essentially a stronger form of the nth term test. So remember the nth term test for positive series said that if the limit as n approaches infinity of a sub n is not 0, then the series does not converge. But for positive series, if the limit as n approaches infinity of the terms is 0, that does not mean that the series converges. The case in point, of course, is the harmonic series, where the limit as n approaches infinity of the terms is 0, but the series diverges. Well, with alternating series, that doesn't happen. You actually have something much simpler. The series converges if the limit of the terms is 0. And it's actually pretty easy to see if the limit of the terms is not 0, then by the nth term test, the series is going to diverge. So this is really if and only if. So this is called the alternating series test. Alternating series test. And it just says that if I have an alternating series and the b sub n's are decreasing and the limit as n approaches infinity of b sub n equals 0, then that series has to converge. So by the alternating series test, we now conclude that the alternating harmonic series converges by the alternating series test, by AST, because 1 over n is decreasing and the limit as n approaches infinity of 1 over n is 0. And that's our criteria for alternating series test. Now, the next questions we have to consider are how accurately can we estimate this series, and what does this series converge to? We know it converges, but we don't know what that series converges to. All right, so let's start with that error idea. So we've talked about error bounds before, an error bound. So error bound means I want to know what this sum is, and I don't really know what it is, so I'm going to just add up finitely many terms, or maybe I'm having my calculator do it, or a computer program. I want to know how many terms I need to use to get a sufficient amount of accuracy. So we call that the error bound. It's the absolute value of R sub n. What it means is the sum of infinitely many terms minus the nth partial sum. So what is the distance from the nth partial sum? If I add up 100 terms, how close am I to the actual infinite sum? I have to use an absolute value in this case. I didn't do that in positive series, because in positive series, the S sub n's are always increasing. But as you can look at this graphic, you can see that the S sub n is sometimes higher than S and sometimes lower than S. So if I want to know the distance, how far away is S sub 4 from the actual sum, I need an absolute value of S minus S sub n. So that's what we mean by the remainder term. Now what you can kind of see is, since I'm always going above and below the term, and the amount I'm moving is the nth term, right? So I'm going down by b sub 2. That means that the error, I can't be any farther away from the sum than the next term is, because the next term is going to bring me closer. So you get this really nice simple error bound that the remainder from adding up, let's say 100 terms, is less than the next term, b sub n plus 1. So if I estimate using 100 terms, my error is going to be less than the 101th term. So that's nice, and I can use that to bound my error. So I'm going to say a little bit more about this, but I want to wrap up this video, this introductory video, by saying, let's come back to this question of what does this add up to? What does that sum, the alternating series, add up to? We know some funny things like sum from n equals 1 to infinity of 1 over n squared turned out to be pi squared over 6, and it takes a very clever person to figure that out. So finding out what they actually sum to is not easy. This one, I don't know. I didn't know what it summed to, so I looked it up on the magical internet, and what I found was astounding. And I'm going to post a link to the page that I found, which gives a very simple, it's simple visually, but you have to sort of put together what they're doing. But it's fascinating how it works. I'm going to post a link to that page in the blog for this, for 317. Are you ready? What do you think it all adds up to? If I add up infinitely many terms of 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and I keep going to infinity, what's it going to add up to? What do you think? ln of 2. Yeah, if you guessed ln of 2, you guessed correctly. Anyway, I'm going to link to this awesome webpage that I found that shows how that comes to be. In the meantime, this is sort of your intro to alternating series. I'm going to do a little bit more in-depth examples in the next video, which you should view next.